Hello and welcome to eCraft. Did you know that the same LED that emits light can also be used as a light sensor? We can use the LEDs on the Microbit's LED matrix display to create a basic light detector. Please take a look at this video to see how you can implement this feature in an Arduino sketch designed for a Microbit board. The Microbit board in the video is currently running the light detector program. You can view the results in the serial plotter window, where you will notice that the red waveform remains beneath the blue threshold line when the LEDs detect light. The red signal is an inverse representation of the amount of light reaching the LEDs. When the LEDs are obstructed, the red waveform surpasses the threshold line. Please note that using LEDs for both emitting and detecting light is an innovative concept. However, it may not be as precise as using LDRs or ambient light sensors. Therefore, it may not be a suitable replacement in all situations. If you're curious about how an LED can be used to detect light, I've included links to some helpful articles and websites in the description box. This method utilizes the parasitic capacitance between the anode and cathode of the LED. When an LED is reverse biased, the parasitic capacitance charges to the voltage applied between the anode and cathode. It is feasible to drive both LED terminals using two microcontroller I/O port pins. Feel free to read through the document at your convenience to learn more. I have also included the reference article link. In simple terms, the section Measuring the Light explains how this works. To make a normal LED work as a light sensor, we need to forward bias and reverse bias it alternatively. This requires both the anode and cathode terminals of the LED to be connected to I/O pins of a microcontroller. It's important to note that the same port pin connected to the cathode should be configurable as an input pin with an internal pull-up resistor. These two conditions must be fulfilled to apply this technique successfully. This part of the document explains that it is necessary to apply a reverse bias to the LED using the I/O supply voltage of the microcontroller, which is typically 3.3 V. This process charges the parasitic capacitor. It's important to note that the capacitance of the LEDs found on the Microbit's LED matrix display has been measured and found to be around 30 to 40 pF, as shown here. Please note that measuring the capacitance requires the positive probe to be connected to the cathode and the negative probe to be connected to the anode. The capacitor has a small value and gets charged quickly. Ideally, it should remain charged. However, if the I/O port pin driving the cathode terminal is configured as an input, the capacitor will get discharged through the input impedance. The time taken for the capacitor to discharge completely is roughly proportional to the amount of light falling on the LED. Therefore, if we can measure the time taken for discharge, we can also measure the intensity of light falling on the LED. The more light, the lower the time for discharge. This is the second valuable source that discusses the technique of measuring light using a standard LED. The article mentioned here was published in Electronic Design in 2007. You may find it helpful to refer to this article. The link to the article is provided in the description box. Unfortunately, the reference codes link is broken. Otherwise, it would have been a good starting point for our sketch. The Microbit boards have a unique advantage for performing this job because they come with an onboard LED matrix that serves as a small display. Moreover, the LEDs are connected to the microcontroller's port pins in a matrix fashion as demonstrated. This allows for easy reverse biasing of the LEDs, which is necessary for this technique. The picture shown here is the LED matrix connection diagram of a Microbit V2 board. Please note that the pin numbers mentioned for the signals tied to the rows and columns are Arduino equivalent port pin numbers. Refer to the previous video if you are not familiar with this already. In this video, I am actually using an older Microbit board, having version 1.5. This board has different connections for the LEDs as shown here. Therefore, if you are using a V2 version, you will need to change the pin numbers accordingly. Also, please note that the positions of the LEDs on the version 1 Microbit boards are different compared to the same for version 2 boards. When the port pins connected to the LEDs are set as output, the default state of the output pins is low. You need to keep these things in mind while developing your program. The program sequence could be like shown here. First, the I/O port signals connected to the rows or columns are set as output. A logic high is driven to the respective row signals and a logic low is driven to the respective column signal. The LEDs are forward biased. Next step is to drive the row signals low and column signals high to turn the LED reverse biased. In this phase, the parasitic capacitance will get charged. The last step is to change the column signal as an input port so that the cathode of the LED sees a high impedance. The capacitor discharges and the voltage on the corresponding column signal drops down. Some point of time, the voltage will become lower than the low threshold voltage and a digital logic low can be detected. This time is required to be measured. The Arduino sketch can be written as shown here. As I am using a Microbit version 1 board for this demo, the LED matrix port pins for the same is defined. In the setup function, the serial port is initialized, the row and the column signals are configured as output ports. In the loop function, the program sequences described earlier is implemented. Note that the LED positioned in the middle of the 5x5 matrix on the version 1 Microbit board is used as the sensor. First, the LED is kept in forward biased for a couple of milliseconds. In the next couple of milliseconds, the LED is turned reverse biased. Next, the column signal or the cathode of the LED is configured as an input. At this moment, a timestamp in millisecond is recorded. The program is awaited till the cathode or the LED remained high. Once a low is detected, another timestamp is taken. The difference from the previous timestamp provides the discharge time. This is also inversely proportional to the light falling on the LED matrix. The last thing is to change the column signal to an output port again so that the next loop can work the same way. The sketch is now ready and uploaded into the Microbit board. We could also see the values being recorded on the serial monitor tool. Note that the threshold for darkness is set as 90, which was approximately defined. As discussed earlier, the discharge time is lower when there is more light falling on the LED and vice versa. The LEDs blink faster when there is more light as the delay is lower. Allowing more light in the room changed the value lower to something between 30 and 40. Now, let me make the room darker by closing the window and turning the lights off. You will notice that the value will increase to something more than 200. Although, in the video, it is not very clear, but you will see the LEDs blink at a slower rate as the delay increases due to more discharge time. This was fun, isn't it? This method is an experimental way of detecting light. Also, we need to characterize the variation with respect to different factors such as component-to-component variation, temperature, influence of spectrum of light outside the visible range, etc. This is something worth pursuing. Share your comments and thoughts, and please subscribe to this channel. Thanks for watching.